demonstrating how industry can also be pushing the state of the art, we have Sekchai. Sekchai is currently CTO and co-founder of Latent AI. Previously, he was a technical director at SRI International, where he led R&D programs for government and commercial clients. And prior to that, he developed imaging and video solutions at Motorola. He received his PhD in electrical and computer engineering at Georgia Tech. His research interest falls in the intersection of embedded learning, embedded machine learning, computer vision, and computer architecture. So Sek, take it away.
Great. Thanks, Kirk, for the introduction. And thanks for the TinyML Summit organizers for inviting me. Pleasure to be here. As Kirk mentioned, I've been around the block long enough, have done work in corporate industry labs, have done work with DARPA, DoD, advanced kind of research, have done work with innovative startups and things. And the TinyML kind of activity and the momentum that it's providing is really, really super exciting, right? And I'm happy to be sharing some of the thoughts I have regards to the TinyML kind of area. The background that I'm providing here is both in the hardware, the machine learning, and also the software. In the previous talk, Diana talked a little bit about the hardware optimizations, go into pruning and things. I'm going to focus a little bit on the software side, right? And more importantly, this talk that I'm giving is going to be a little bit forward-looking, right? The goal here is to kind of inspire kind of thinking about where we could go next, right? If at the end of the talk, you come up with more questions, right, than answers, but you feel motivated that there is a lot of room to grow within TinyML, then I've done my job, right? The talk is about adaptive neural network for Agile TinyML. And I go into what I mean by adaptive and what I mean by Agile. And hopefully you get the gist of it at the end of the talk about where TinyML could be heading. So within TinyML and how it intersects, there's kind of tenets about things that we want to look into. I put kind of these three items together: robustness, agility, and efficiency, right? And robustness really means accuracy. How well can we meet the task at hand, right? Is it classification, detection, those kind of things, right? Can you maintain the type of accuracy that you want for the task at hand? You're building these kind of TinyML machinery. Can it do the job, right? And we have a partner session that talks a little bit about that. I'm going to talk a little bit about agility and what does that mean, right? How do we adaptive across different workloads, right? And how do you kind of maintain and what do you look for with respect to agility? That's this talk. And then tomorrow we have another talk in the research symposium that talks about efficiency. And in that case, we talk about quantization and training, and we talk about how do we make it as low power as it can. But really, it's a combination of all these three: robustness, agility, efficiency. They go hand in hand. There's intersection points for each one of these, and there will be design points on all of these kind of spectrum. There's a lot of criteria. The edge itself is not well defined. There's device edges, network edges, and machinery of all different sorts, different tasks, different requirements, right? And there's the ability for us as designers to go between these kind of tenets that I've opposed, right? Robustness, agility, and efficiency. So let's focus a little bit about agility and kind of go deep dive into what that means. And we'll start very, at the high level, and everybody is kind of aware of this. We talk about this. The whole symposium is about AI coming to the edge, no doubt. We've seen all sorts of variants. This is another smartwatch example, same with what Diana had. The idea here is that AI that's been running on the cloud, right, can be transformed into a small form factor to run on edge devices. We know that TinyML needs to be efficient, right? And we know that these are going into devices that are small, they are mobile, they're agile, and all those kind of properties that we want. And this is going to transform the industry in terms of what smart machines can be enabling our daily lives, right? We all understand this. And if you look at the challenges that we are addressing today, these are the common kind of metrics that we kind of fall under, right? We're trying to reduce latency. For example, how fast can the AI machinery turn around to give us an answer? So low latency will be an important key metric, for example. And this would be in comparison to sending all the data to the cloud. Edge devices, with respect to TinyML, process things close to the sensor where it is being captured. So the latency is definitely reduced without going through the network kind of traffic and bandwidth issues that you might address. We know that there's limited compute. We don't have wall socket power and things like that. It may be battery powered, there's limited space. So limited compute is another challenge for TinyML. Same thing with memory footprint, right? We don't have many gigabytes like in a data server, but small footprint, reducing bit precision, all those kind of things that we all about. That's another constraint and metric that we are going after. Power comes along as well, right? Again, battery powered means you got to be very judicious in terms of how you want to spend your energy, right? If it's battery powered, and you want to be very careful about how you use that. So these are the kind of metrics that you go after. I put in security as another kind of challenge for TinyML. Typically, folks don't kind of look into security until it's needed. Security, we always want it, and we want it for free. But it is there. It is there that I think the TinyML community can look into and will look into as time comes, right? But it's certainly challenges for TinyML today. I would also suggest that the current tools and hardware today are focused on these metrics, right? And they are addressing all these challenges. They're going about in many different ways, but these are the things that are all in our minds today. The question then goes into, can we squeeze out more efficiency from what we're doing today, right? Our current approach with respect to all the metrics that we talk about, latency, power, compute, and all that, can we get more? Can we get more efficiency from how we are going about solving that problem, right? And can we get more out of it by leveraging, for example, how the inference is done? What are some dynamic aspects when we do a neural network inference? So I laid out some examples here where we say, okay, if you look at the spatial, temporal, and dimensionality of the things that we want to process, maybe there's some things that we can leverage off. So for example, in a drone video surveillance perspective, you're looking for a vehicle driving here. If you look at it, most of the scene are very similar, right? You're looking at grass, but in fact, you want to track the car, right? The car is tiny within the field of view. Is there something you can leverage from that spatial redundancy, right? From respect to how to squeeze more efficiency from your compute. Same thing with some sort of temporal nature. If you're doing surveillance type video, you're looking at a scene, in most cases, nothing's really happened. There's no motion. And if you're looking for people in a parking lot, maybe nobody shows up and you're running still high fidelity, right? You're burning power to do the type of compute that you need. What can you do to squeeze more efficiency from there? And from a dimensionality perspective, you look at a spectrogram, for example, the signal of choice may be in a very kind of small area, right? You may be scanning throughout to find that signature, but in most cases, it's very kind of structured and it's kind of placed in a certain area. Again, can you squeeze more efficiency by understanding that domain? And it is this kind of level that I'm suggesting for the community, leveraging the dynamic aspect of the inference that I think we can squeeze more out. And that's the next level of kind of compute that we can work after. And that's what I mean. And we'll talk about agility and adaptivity for these kind of applications. If you switch gear a little bit and say, what are the type of hardware accelerator? How are we building the hardware to do the workload that we want? And today, what we typically build are accelerators that are mainly kind of doing static control flow. You might have a deep network, and you're processing things in a very structured way, statically defined patterns, one layer at a time, and you feed it through an accelerator. This is pretty much data flow and data parallelism that we are leveraging. And those are the very easy ones. And those are very well structured. And you certainly can get a lot of performance gain from it. I showed an example, TPU, Tensor Processor Unit from Google, and certainly many other styles and architectures that are being built today, right? But predominantly, I would say that most hardware accelerators are designed for this static control flow, okay? And my supposition is that from the previous slide, how can we squeeze more efficiency from this is to leverage the dynamic aspects of the task at hand, and we'll go into what that means. So if you look at what it means in terms of optimizations, the traditional ones would be pruning. We talked about that in the previous talk by Diana. And there might be quantization. You're trying to take floating point representations, bring it to integer. You might even go to binary type networks, right? With respect to dynamic and adaptive, what we're looking at is then the ability to throttle, the ability to kind of understand that not everything is activating in your neural network. In fact, the type of activations is pretty sparse. And the question is then, how do you leverage that? And how do you then bring the compute around to compute only the nodes that you want at runtime, right? It's a very challenging thing because you designed the neural network to be sparse to begin with. And then you say, can the compute then match how it's actually activating, right? So this is a challenging problem, but there is where some opportunities will come with respect to what we mean by throttling, and I'll go into that. So the idea here is that there is some sparse activations in this network, and then can we leverage it? Now there's some circuitry and network and design regarding spiking networks. It's related, but I would say that the classical deep learning kind of approaches can still also kind of leverage that sparsity and activity there, right? So in a way of summarizing these kind of differences in terms of the traditional approach and what I would mean by adaptive in the AI sense is really things that are statically defined during training and what could be made dynamic at runtime, where in fact at runtime after training, you're deciding how you want to run the network. How do you train the network to leverage that activity and the sparsity at runtime, right? And we'll cover a little bit about that. So with all that in mind, and we talked about how the neural network is activating and it's sparse and all that, what are some basics in terms of what I mean by dynamic inference, right? What are some kind of major components that one should look into? And again, this is still a lot of active research in here, but I would generically call these kind of components. You have the deep network. We understand that it's activating. You can have all sorts of different activation functions, ReLUs and things like that, but in general, it is sparse. And I show that with some kind of green shaded link there. Those are the activating patterns, right? And recognizing that means that you put in a control network, some gating control, right, to figure out, okay, what parts of the network you really want to be activating, right? And that would be analogous to some sort of attention mechanism within your deep network that you want to run. So that is this control network, and it's a little bit kind of guiding, in fact, the inference that we run on a deep network, okay? So you add a little bit of control mechanisms alongside the deep network to help you get the efficiency that you want. Now, some of the things that we want to pay attention with respect to literature that's coming out is the differences within what we mean by this control network. I'll focus a little bit more on things that are, I would say, context dependent. That in fact, that control network has some sort of input built into it that is actually understand what the context might be with respect to the data that's coming in, that's feeding into the network. You may get a preview of what that might mean, and that will help drive how you want to activate the deep network. And I will say that the deep network itself is the selection of what you want to run is made at runtime. So that starts to differentiate this set of approach from, let's say, network architecture search, like NAS kind of approach, where you do actually do a selection of the right set of parameters, but you're really doing it at training, right? And you select a set of configuration, and that configuration is kind of deployed out, and that's what you run. When in fact, what I mean by dynamic inference is that you don't really need to prune out or select a configuration. You make that decision at runtime, right? And you have some sort of control network that's context dependent that helps guide what it needs to run. So quite challenging in respect to having yet another set of control network, and how would you go about gating some of this deep network, right? Can it be done? Now, I want to show a little bit about hardware. How are we able to use some of that concepts about dynamic inference into today's hardware, right? So I've kind of structured it into fine grain and coarse grain, right? Fine grain could mean like if you have a model today, you have tools that you can slice these networks up into smaller chunks, and those chunks are run in an accelerator, and then you can decide what chunks you want to run, right? Slices of the tensors that you have. So today, in fact, you can operate your accelerator that way, and then you can get some performance by being smart about what slices do you want to run, right? From a coarse grain kind of perspective, similarly, you may have a deep network, maybe it's built like an ensemble, and you can be able to split up these networks into kind of smaller ones. And perhaps it's a wake up and a host type system where you say, I want my system to wake up only with a set of priority, a set of classification nodes or whatever done, and that wakes up the host to do most of the rest of the work, for example. So again, tools can be made to split these models up into smaller nodes, activating things that you want, but split into different pieces of hardware, right? So with this in mind, all I'm saying is that dynamic processing can be done today, right? Not easy, but I'm saying that there will be more efficiency gains in the future as hardware adapt to the understanding that, in fact, deep networks doesn't need to be a static control flow, but in fact, it can be dynamic, and there's a lot of things we can leverage from how we built the hardware, right? Even this alone, if you look at how we go about building multi-threaded type architectures, right? We built in control engines and things like that to extract instruction level parallelism and all sorts of task level parallelism, when in fact that is being done really well with the CPU and the accelerators that we do. Can we use it for deep networks? And my suggestion is yes, we can, but it takes both a change in the concept in terms of how you built the network and also how you would build the hardware. Okay. So all that in mind, we talked about what it means by dynamic inference. We talked about some hardware that we can apply it to. Let's look at some models, right? Let's look at some examples about how do people do it today to train a network such that you have an anticipation that at runtime, you select the right filters, the right pathways to execute your networks. And I show some example here that many others coming, right? It's still, in my opinion, a kind of a very new research line, right? And people are getting into the understanding of what this is. So I'm selective in terms of picking some examples here. I would say there's a few more that complements the set, right? In the leftmost, there's a network called GatorNet, where very traditional kind of deep networks that you may have. We call that a backbone, and the GatorNet control network sends a set of control signals to that deep network, right? As I've shown you, a very kind of vanilla classic dynamic inference engine, where you have a controller engine, and then you have the kind of deep network backbone, right? That does the main task. The difficulty here with respect to this network, the GatorNet, is that you have a lot of control signals, right? The deep network, the backbone itself, may have a lot of different nodes, and how many signals do you need to go into it to gate or select the different modules? So it's a nice concept, but there's still a lot to kind of optimize from there, simply because of the kind of type of control signals from the controller to the backbone. In the middle here, I show another good example called slivable neural network, right? And in this case here, it's just changing the different bit width. In this case, it may be, let's say, a mobile net, and mobile net comes with different kind of configuration for different channel width. You could train the different channels to be turned on and off, right, at runtime, right? And slivable neural networks talks about that, where you may have a full configuration, but you can select a different bit width, right? And you have to train each of these channels to be robust with respect to the task at hand, to be able to scale up and down. And the difficulty here that I've seen is that the channel capacity drops off really low, right, really fast, meaning the accuracy starts to drop off really fast because of the type of task at hand that you want to do. So for ImageNet, for example, it rapidly drops off in terms of the accuracy. And I think it's due to the way that the channel width it's kind of selected. It's a little bit more too structured in that way. On the right-hand most, and which I will talk a little bit more about, we have a paper in archive, and folks can look into it. A lot of the details that I'll be presenting is in this paper, so I'm suggesting folks to go in and read more about it. But I'll give you a high-level kind of overview of what we're talking about with respect to what we call a throttleable neural network. Same concept here. You have a controller, right, network, and that drives some inputs into the throttleable network. We call it TNN. And the TNN does not mean necessarily structured on kind of channel width selection, but is actually a conglomerate of nodes, right? Some selectable parts, modules, and things like that. And it can cross across channel boundaries, right? So you have these selectable parts, and then you have a controller network that drives it. The main difference here that I will say is the concept of the utilization, right? This signal that goes in. We no longer need to drive a vector of signals that are wide and large. We can actually select what we call a single scalar, what we call utilization. That simplifies the way you would train the controller and the way you would kind of organize the throttleable network, right? Makes it a little bit simpler to drive and control what you need on the backbone network, right? So this is kind of a range of modeling examples. And if you look at it and say, okay, what does it mean? Again, what are the differentiation for all these approaches? Is that the amount of processing is determined dynamically at runtime. You train it in a certain way, but at runtime, you decide how hard you want to work. Applications, in this case, will have the choice of how hard you want to work. That could mean a lot of things. For example, if there's nothing in the scene of interest, you can dial down your neural network. If your battery is low, you may choose to give you a different quality of service. If your network bandwidth is challenged, you may choose to run your neural network differently. So context dependent and having the application the choice of making that selection at how hard you want to work gives a lot of range in terms of the applications that you want to build. And that's where the kind of efficiency come back. We go all the way back to saying, what do we leverage here? We understand that each domain, each application has a different context, and now you can build your neural network in a way that allows you to throttle or dynamically adjust, right? So if you go now into say, okay, really, that's a great idea, that's a great concept. How do you actually train it, and how do you work about the controller and backbone network? What does it all mean, right? What does it all mean from a developer perspective, and how do you really get the performance, right? Show me what it could do. So I'll go through what's in the Throttleable neural network paper. There's 2 stages of training, and I'll go through some examples and some intuitions about what it means, right? So in the first stage, you train your backbone network, right? You can select your module width-wise, depth-wise, independent, nested, different kind of configuration. Again, modular blobs that you call and partition out, and say these are the kind of areas where you kind of partition out what could turn on and off. So there's a little bit of training and kind of configuration, and you kind of have a set of networks that is trained, and it's anticipating that not everything is turned on, okay? And then there's a second stage to the training, what we call a controller training. And this could range from very simple heuristics to reinforced learning to train what parts of the backbone network that you want to turn on. And we'll go a little bit deeper in the next few slides about exactly how you do that. The main point of this slide here is that we are doing the training separately. We're training the backbone in one stage, and then we're training the controller in a second stage. And that actually is an important kind of distinction, because we're trying to decouple what the controller might need to do and what the deep network is trained to do. If you do it jointly, then it's pretty static, and you may have a kind of very less context dependent kind of design, that your controller itself may learn some aspect of what the data network needs to learn, right? And then you complicate the controller in that sense. By decoupling this, then we have the choice of changing the controller at runtime, right? You may have a deep network that is trained for certain tasks, but you may have different contexts or different kind of situations where your controller itself can be swapped in at runtime. right? For example, you may have a situation that you train this deep network, and at first your main goal is to give you the best latency. So you load in a controller that is game for giving you the best latency. Right? How would you go about turning on different networks to get you the best latency? At a different situation, you may have a kind of battery, low power battery kind of constraint. You want to save the most energy. So you load in a different network that may be game towards saving you the most power, right? So the different controller would run alongside with the backbone, but is actually tuned to do an ulterior reward system, right? An ulterior kind of goal that's set. So decoupling the network allows you to then have the ability to swap in different controls, right? Okay. So then let's look into some basic intuitions about what the deep neural network can do, the backbone itself, right? And here's a very simple example. We start with that first. ResNext model CFAR10. So very simple model and very simple kind of data set in a sense. But what does it tell you, right? And we have different kind of different gating policies and things like that on the top two graph right here. And what you see is that as you start to gate more of the network, right, from 0, meaning you're not turning anything off, and to 1, which is 100%, things are all turned off, you start to level off. The accuracy itself would drop off. For a naive training, right, meaning you simply didn't train it the way we suggest for you to train, the accuracy would drop off right away, because there is parts of the network that when you start turning it off, you start to break down the results that you would get, right? There's a dependency on some of these filters that to be on at all times. And if you turn those things off, the accuracy would obviously go down to something random, right, at the bottom. Whereas if you train it the way we have suggested with kind of approaches for these Throttleable network, you can actually sustain the accuracy even with dropout, right? And the way we train it is with runtime dropout. So as you train it, you randomly choose blocks of these networks that you have defined, and they're off, right? Which means then the representations within the deep network is no longer dependent on one single entity, one single module to be on. We disentangle the representations then, so that it is by itself independent, and then it itself does not rely on the other one being on, right? So we're spreading that information around such that no one single module is going to be the critical path, let's say, right? This helps in a way for forgettingness, because you're no longer one set of filter that is going to drive everything, right? And the whole premise here is to reduce computation, right? We'll talk about that with respect to power and things like that. One key thing that you want to note is at the point here where there's zero gating, right? Zero gating here. And you can see that the naive training, right, the way that we train today may get a higher accuracy rate at zero gating. So if you naively train, meaning the traditional way of training it, you may get a filter that is going to give you the best choice, right? The best answer, best accuracy. But with the Throttleable kind of approach, because you're spreading the information around, you're choosing other filters that may not necessarily give you the best, right? And that's the trade-off that we are saying. By trading off some accuracy at 100% utilization, right? You're able to kind of sustain that accuracy as you turn off more of the network, right? So those are the things that I want to look into. Well, hopefully this slide kind of gives you the basic intuition of what we mean by the Throttleable network. On the controller side, right, similar things. You can have very simple kind of heuristic codification. It could be as simple as an if-then-else kind of structure. If one scenario happens, I want to run it 100%, or it's 50%, almost like a case statement. It could be as binary as saying, time of day, daytime run it this way, nighttime run it this way, and that's it. Very simple, right? And those can be kind of very easily codified. It can be data-driven, which what I've shown in the right. And there's a lot of ways to use, let's say, reinforced learning. In this paper, we talked about a contextual arm bandit kind of thing to train the network. But suffice to say, what it means is that you have in your backbone network many different modules that could turn on. And we use reinforced learning as a way to almost like a game type approach, right? You're trying to figure out, based on the reward that you have set, what are the things that need to turn on? It's a game. You're going to explore and try different kind of things that turns on, and does that give you the best reward, right? And the reward can be many different ways. We can train a controller for latency. We can train a controller for best power optimization for the task, right? So different controller can be trained based on how you have the backbone set up, right? And what it drives out is the utilization in terms of, okay, given this state, given this condition, and I want to now maximize my reward based on the change of input set, can I now turn on these set of networks to get me the better accuracy and then dial that back down, right? So it's a very straightforward kind of reinforced learning, but it is kind of conceptually complex in understanding what you mean by the state that you want and what a state that you're going to. But suffice to say, putting it into the description of a game kind of concept, it is like exploring out what pathways you want to run on your deep network, right? So controller design is, I think, very interesting, and I think it will grow, and it can go from a simple heuristic to kind of data-driven approaches. Many different things here that can be looked into. So then, you say, Sec, that's interesting. You showed me some results, CFAR10. That's too simple. Like, let's look at something a little bit more complex. And here are a little bit more results from ImageNet to Pascal VOC, where you kind of have larger classes, larger networks. And what you see is that the same kind of behavior, right? What I've done here is, instead of using the word gating, which may be more implementation specific, I'll start to use the term utilization. How much of the network are you utilizing, right? From 100% to zero, and close to zero. We understand that by the time you get closer and closer to zero, you're turning most of the network off, and it's likely that you're not going to get any performance. But the point is, at a certain threshold, maybe even 50% or a little bit more, you're still getting good enough of an accuracy, right, from how you have trained the network and how it could run at runtime, right? The dashed line on the bottom here suggests that all the naive training approaches drops off immediately, much like what I've talked about in the CFAR10, right, example. So the same behavior from using the training approach that we talked about for training network, for CFAR, but also for ImageNet and larger kind of problem set, right, larger models, larger problem set. So that's a good thing, that TNN can be trained to be robust to runtime gating or utilization, right? Okay, so if you believe that, then say, okay, that's a premise in terms of what we mean here. What does it get you from the metric that we're concerned about? We talked about power, runtime, and latency. So here's an early result running on an NVIDIA Xavier AGX kind of system. And what I want to show here, most important, is the coupling between the accuracy, power, and runtime. What does it mean as you start to change your utilization from 1 to, let's say, closer to 0, right? What does that actually mean from a savings, power, and what do you get back in terms of runtime? So what you see here is that as you start to change the utilization level, right? Different parts of the backbone is now being gated off. The accuracies kind of maintain its level, right? It's maintaining its high level, close enough to the kind of peak, right? Before it levels off. But what you see is, in terms of the power and the runtime, it's kind of linearly reducing. So that makes sense, right? Because you're turning off parts of your network, you don't need to consume as much power to process those nodes. The runtime also kind of decreases, and your latency improves because you're not spending the time to compute it. So that's the benefit you get, linearly reducing, say, the power and the runtime, but your accuracy is maintained, right? And then it's all about saying, what utilization level do you want to run, right? In terms of the performance, right? The application has a choice to run it at 50%, 60%, and what have you. Okay. So that's good indication. Now we've seen networks can be trained. It can be kind of complex kind of results and complex kind of data sets and things. And in fact, there is some gains with respect to hardware today. So let's work on problem sets that are a little bit more challenging, a little bit more realistic than just CFAR or ImageNet, right? And what I'll show next is some example videos and things that goes into problem sets that we're interested today, right? And what we'll show next is a gesture recognition problem. So we're doing video and we're looking at gestures. And what we have set up is an application that you have video coming in, and there's a couple of things that's running. On the top, the video frame comes in. We have a pose visualization. So you see some skeleton kind of overlay based on the input. You have a data network that we made Throttleable, right? And this looks into the gesture. We have a controller network that we have trained. It's handcrafted or trained with reinforced learning. And the results we showed in the paper that I've referenced. And then we have a little bit GUI and saying, what is the actual throttling, right? Because you need to kind of internalize what's happening within the neural network. So this is a gesture recognition application that we built as a demonstration vehicle, but it kind of highlights that, going beyond CFAR and ImageNet and the simple kind of toy kernel examples into something more realistic. And here we show the example here where you have the throttling happening on the onset of a gesture, right? The network decides I need to throttle up because I'm not getting the confidence that I want. So it will throttle up to a higher level, get the confidence that you want, and then throttle back down. What you see here is that the throttle meter itself is not always at 100%, right? It actually have a range of utilization. This is U scalar value, right? That changes based on the context of the scene. If it's not doing any gesture, you don't need to run high. When a start of gesture start happening, you can actually throttle up and get the result that you want, right? You can throttle down to 30% when nothing's really happening. And at 50%, we only see like a 10% loss in accuracy. So that's very appealing to the application developer, right? That there is a choice in terms of how you want to run your neural network, right? And you can actually game it so that you can say, are you sensitive to latency? Are you sensitive to power? And then control it the way you want, right? Based on the application that you need. Okay. And this video is available on YouTube, and we have kind of blogs and papers. So feel free to watch it as well. And I'm sure this keynote is also recorded. Now, with respect to insights, right? One thing you can look into is for the different gestures, how does it behave with different utilization? Or how does the accuracy change if you have different utilization, right? And for different gesture, what does it mean? So what you see here is a kind of a study saying, given, let's say, a stop sign kind of gesture, right? You probably need a little bit more high utilization on the right-hand side before you get good enough of an accuracy. As opposed to, let's say, this gesture, pulling 2 fingers in, right? You don't need that higher level utilization to recognize that gesture. So different gesture itself, given the same network and the way we trained it, you can have different utilization. So, and the onset of a gesture, you start to realize, hey, I can actually game it because I understand it's more likely to be, this gesture, pulling in the 2 fingers rather than a stop sign. I'm going to start using this utilization level. You can actually change the utilization level based on, some context, early context in terms of how you want to recognize the gesture and what have you. And you can go through a sweep of different gestures and say, okay, how do I then recognize the gesture or whatever object by being creative about how you want to go about addressing the task at hand. Okay. So different gestures require different number of features, and that means different level of throttling can be set, right? And you can be very systematic about designing a controller that is adaptive to the operation. Okay. And showing a little bit more interesting examples, here is a object detection, a surveillance video kind of scenario, and we're running this on a Raspberry Pi, right? And when there is nobody in the scene, you don't need to run it high. And when there's somebody in the scene, you can start to throttle in and out. And what you see is in the throttle meter here, you don't need to burn it high in terms of the compute, stressing the Raspberry Pi, for example, right? We can throttle in and out. Given the same network, train in a way to allow you to throttle, you can have this system where it kind of games up and down, saving the power and compute only when you need it. Right. Now, what that does is then you start to understand, well, there's some premise to the way that we do dynamic inference, adaptivity and agility, right? Why aren't we seeing more of this right now? So I have a few slides to kind of end, but what I'm suggesting here is that we need to start thinking about what it means in terms of the ability to understand how well it's doing, right? The metrics for agility itself needs to be explored. Benchmarks have to be kind of created because this is a different approach. You're no longer looking at peak accuracy, but sustained accuracy. You're no longer looking at just your memory footprint, but your working footprint. How much of the network are you really running and what are you really loading into the network, right? What is the recovery time? We anticipate that there will be some time before you get the good enough answer. Is it fast enough? Is there a recovery time metric that needs to be there? And not just power, but energy consumed, right? Because that's really what it is. If you have a different envelope in terms of how you go about changing the utilization, that gives you a kind of total energy consumed. And maybe you can be creative there. So the suggestion here is that the community needs to understand that there are new metrics that need to be provided and understood, and that will start kind of grow the concept of how do we understand if these dynamic networks, these adaptive networks can really work well. Okay. And a lot of work can be done here, and there's a lot of good activity going in terms of benchmarking networks today, and I'm suggesting there's more that we can do. And from a development flow perspective, what are some tooling that needs to be there? Here's an example where you may pull in a large model and out come a tiny model, right, for any hardware. And this kind of tooling and system like this may have a template in terms of what it does from a controller perspective and the Throttleable network, right? Can we build models that once we deployed onto the different hardware, it is adaptive in mind? The application developer doesn't need to worry about how to cart things out, but use a tooling to be able to go through the process and create the runtimes that is adaptive, right? A lot of these things are what we are addressing at Latent AI, and these are the challenges that we are kind of addressing. Okay. So I'll end with this slide saying, dynamic networks can enable kind of new design targets. New hardware and software tools can be built, and I think there will be a lot of things that can go from there. We talked about Throttleable networks, but many things are coming down the stream. I'm looking forward to seeing a lot of these, and hopefully drive new capabilities, new things that can be done for TinyML. A shout out to the team at Latent AI. We've gone through a lot of awards and things like that, but we're addressing challenges for TinyML. Right. I'll just end with that and see if there's any questions on the floor.
Thank you very much, Sek. That was a very stimulating talk. So we have a number of questions from the audience, but again, I'm going to use moderator privilege here. Mm-hmm. If you could go back to your slide 6, you talk about how current generations of accelerators are, I think it's slide 6, are set up for static scheduling. Mm-hmm. And then in the remainder of your talk, you talked about dynamic, but I didn't exactly get how for these current and on soon to be released generations of accelerators with large multiply accumulate matrices, which are all statically scheduled. How will your dynamic techniques work on that hardware?
Right. So we what I've described is mostly on the software side, right? And somewhat dependent when you say power, it really depends on how the hardware mechanism computes it, right? It is most of the accelerators today are built in a way that says, given this tensor computed, and I'm kind of very well bound in terms of that scheduling of that static network. For adaptive kind of networks, then we need to start carving this out. There may be parts of the network that you have higher priority and whatnot. So you can use today's accelerator, right, by tooling from the front end side and carving out the networks that needs to be run. So you need to be smart about saying, okay, these are the piecemeal piece that you need to run, and you may build a kind of wrapper code around it. So think about, you may have one big monolithic network, right, as a piece of code, let's say. You're carving it out into half, and you may have an if then else kind of conditions to decide what parts you need to run. So you can use today's accelerator. What I'm suggesting is that new hardware that have more of the hardware support for contextual kind of swapping can get you a little bit better performance.
Mm-hmm. Okay. And so that swapping out and so forth, that would be done on like a control processor on the side, deciding what to actually populate in the multiply accumulate matrix and so forth. Is that
Could be. So if you have a host and accelerator, like an ARM or x86, whatever CPU, and you have a hardware accelerator, that host have to do that contextual swapping, right? And that's what I mean by, yes, you can do it today, not as efficient as you like because it's not tightly coupled yet with the accelerator. But if in the long run, the accelerator itself have that notion of contextual swapping and whatever, you start removing some of that burden away from the host into the accelerator, right? So today, you could do it today. You have to carve things out and have the host kind of assemble it again, right? And in the long run, once the accelerators are built more for this kind of dynamic operations, I think you'll see more gains.
Great. So you have quite a number of questions, and I'll do my best to navigate them. First is the accuracy of the controller, the GatorNet, affects the accuracy of the throttle network. If the controller has high error rate, the throttle network will suffer significantly. How do you maintain high accuracy for TNN? And let me also say before you respond, we have easily 5 questions here. So if you want to, I know you could probably go on quite a while on any one of these, but if you give a kind of crisp answer to each, that would be. We'll try and
so
get
it's
through
application dependent, of course. And I think you can always run it at highest utilization. If you don't turn anything off, that's the accuracy you get. So it's a choice in terms of how you want to adapt and respond to the answer. That's why the metric that I talk about in terms of the response time, that actually has a play in terms of how you want to build the controller.
Mm-hmm. All right, thanks. And then Barry DeBruyn that's a good question. He thanks you for your interesting talk. So you present results on BGG, ResNet, and so forth, popular baselines, but compared to MobileNet, they're very overparameterized, right? So what kind of results do you have on more, kind of nets we might expect to see at the edge?
Many more. But much like anybody, we are resource constrained. So I'd love to kind of go offline and talk and see what the individual requirements might be. Select the type of network, and then we can work with you. I think that's the best answer I can give.
Okay. And Mo asks, wouldn't redundancy among maybe if you could turn to slide 12, wouldn't redundancy among the network components layers increase with the suggested disentangled training?
What was the question again? Sorry.
Yeah, so if you want.
Okay.
So I'm not honestly sure that I understand it myself, but wouldn't redundancy among the network components or layers increase with the suggested disentangled training?
Yeah, and that's a very interesting question about what actually are we doing. So what I'm suggesting on the disentanglement is that you are you're trying to kind of sparsify that information so that no one filter or no one module is dominant. So that suggests that there is information that you are spreading around that is required for the task, right? So it's like not clustering, but the inverse of it for runtime adaptivity, right? And you can change the models and type to kind of adjust for that. I would suggest that what we're trying to do now is understand what we can do with current models. And I would leave it to the community to say, can you build a model for adaptivity, right? For this runtime kind of component, rather than only rely on the networks that you have today. Great things have been done with MobileNet, SqueezeNet, and all those kind of things. Can there be kind of new designs coming out, especially with the controller in mind? So I leave it back to the community to say, don't stop at what I'm showing, but there's more you can do.
Okay, and then maybe just one more. It's a kind of multi-part question, I think. So how does the throttle network gating threshold change in inference? How do we know how much workload we should carry out for a particular input? And I guess I would tack on that. You didn't talk too much how the gating network is trained. And in the examples that I'm thinking of, like, yeah, we'd love, say, an autonomous vehicle to just kind of chop out the sky quickly and then not keep recomputing over and over with regard to that. However, that a little bit begs the question. You've got to do the identification of the sky. I've seen networks where you can do that in parallel, but to be entirely able to pre-compute it, that I don't understand. So,
Right.
answer. I think you see what's being got at here, so just answer it however you like.
Yeah, and we face a lot of these kind of similar questions, right? Because you're trading off what you mean by immediate answer and what you could trade off from a time perspective to respond to an answer. So my suggestion would be like in the autonomous kind of driving scenario, right? If you're driving and something swerves in front of you, first thing you do is you try to avoid it. You don't necessarily need to know, is it a car, is it a bike, or is it a pet, right? And then you say, oh, what was that I missed? So if you have that notion from how you drive, can you build a neural network that says, hey, I'm going to be fast and low latency, right? Because my whole point is to avoid collision first. You say, okay, I'm going to scan my field of view, and it could be wide, and I'm going to do it as fast as I can. But once I say, oh, now the situation changed, and I need to now go into a mode where I have a little bit more fidelity of what I'm looking at, you game up the throttling, right, to get you the fidelity if you want. It doesn't matter if it's a cat or dog, but you want to miss that dog, right, or cat. You have the fidelity that you game up as you respond to that incident. So those are the concepts that we are trying to build into the application itself.
Great. Well, thank you very much, Sek, for a very stimulating talk.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotg, and Synsense.